Mass-producing a commercial beverage requires pouring millions of liters of liquid every single day. Yet within that massive volume, every individual bottle must contain the exact same chemical composition. In the case of aqueous energy suspensions, the factory relies on continuous flow fluid dynamics. Conversely, producing solid herbal digestive compounds requires batch process solid-state mechanical compression. Extracting a dry compound from raw agriculture and suspending active chemicals in a carbonated fluid demand two completely divergent industrial pipelines. Regardless of whether the final product is a pressed solid or a liquid solution, the manufacturing objective is identical: managing a strict biochemical payload. If a facility miscalculates a mixture or allows ingredients to separate, the resulting dose will vary drastically, leaving the product either metabolically ineffective or biologically dangerous to the consumer. Scaling up a consumable requires the rigorous application of fluid mechanics, thermodynamics, and solid-state engineering to guarantee the product matches strict human biological thresholds. The continuous flow liquid pipeline begins with massive-scale industrial water purification. This diagram shows a microscopic cross-section of a semi-permeable membrane. High pressure forces raw water against this barrier, allowing small water molecules to pass through while physically stripping out dissolved salts and chemical impurities in a process known as reverse osmosis. The water then undergoes biological sterilization. Ultraviolet or UVC light waves penetrate the fluid, specifically targeting and destroying the genetic material of any surviving viral or bacterial pathogens. Once the baseline liquid is completely purified, the factory transitions to active formulation by creating a thermoregulated syrup base. Mixing this base is governed by strict thermodynamic constraints. If the temperature is too high, the molecular structure of the sucrose degrades. If the temperature is too low, the fluid cannot reach complete solute saturation, leaving undissolved sugar in the tank. With the base stabilized, the first active biochemical payload is introduced: caffeine, formulated specifically for central nervous system stimulation. Next is taurine, an amino acid integrated to support ongoing neuromuscular function. The third component is a synthesized vitamin B complex, which acts as a metabolic catalyst to convert ingested calories into usable biological energy. The final active component is a high-density sucrose load, calibrated to force an instant metabolic energy spike upon digestion. To ensure this complex chemical mixture tastes exactly the same in every batch, flavor scientists override natural agricultural variations. They deploy highly concentrated artificial flavor molecules alongside trace natural extracts, locking the liquid into a strict, reproducible baseline taste profile. This sequence of precisely measured chemical formulations guarantees that every single unit delivers an identical pharmaceutical-grade active payload, regardless of where or when a consumer opens the bottle. The formulated liquid undergoes physical conditioning to survive shipping and storage, starting with atmospheric manipulation via high-pressure carbon dioxide injection. Dissolving CO2 gas into the fluid creates the required carbonated suspension. This gas remains trapped in the liquid until the seal is broken. To guarantee extended shelf stability, the factory applies an extreme thermal process known as pasteurization. This line graph plots the exact pasteurization parameter applied to the fluid. The temperature is forced into a sharp spike to exactly 90 degrees Celsius, held briefly to eradicate any lingering resilient microorganisms, and rapidly dropped back down before the suspension can boil. Even completely sterile liquids carry the inherent physical risk of stratification. Over time, active ingredients in syrups possess varying molecular weights, meaning they will naturally separate out of the liquid suspension and settle into distinct layers. The fluid mechanics solution to this separation problem is industrial homogenization. Extreme mechanical pressure forces the formulated liquid through microscopic apertures. This violence breaks the large, clustered particles down into identical, uniform microparticles that will never separate. The homogenized fluid is then routed directly into the final bottleneck of the pipeline, the automated, high-speed bottling matrices. These mechanical capping matrices operate at high velocity, sealing hundreds of units per minute to guarantee the sterile suspension suffers zero atmospheric recontamination. Without the application of extreme thermodynamic spikes and violent fluid dynamic homogenization, the carefully balanced chemical suspension would spoil or separate long before it ever reached a store shelf. The closed-loop liquid system operates in stark contrast to solid-state manufacturing, which relies on highly variable raw agricultural inputs sourced from arid climates. Raw biological crops carry unpredictable flavor profiles and excess internal moisture. They require immediate thermal activation upon entering the facility. During the desiccation process, massive industrial roasters heat raw cumin and heavy spices to exactly 130 degrees Celsius. Hitting this specific thermal threshold achieves a dual purpose. It rapidly vaporizes excess water weight, while simultaneously forcing the plant cells to release their dormant, volatile flavor oils. Once desiccated, the dry organic matter requires multi-stage industrial grinding to facilitate precise chemical compounding. The engineering tolerance at this stage is absolute. Automated sifting mechanisms constantly filter the output, isolating and forcibly regrinding any particulate larger than 3 millimeters. If the particulate size varies, the active biospices will fail to mix uniformly. A poorly blended batch creates dosing variations, resulting in tablets that are either metabolically ineffective or dangerously concentrated. This animated wireframe illustrates the final transition from loose powder to solid structure via mechanical compression. The rotary press uses intense downward mechanical force to crush and bind the dry particulates. This extreme pressure fuses the uniform dust into a cohesive solid structure without relying on any liquid binders. Where liquid engineering forces chemicals into suspension to prevent separation, solid-state engineering extracts moisture and uses brute mechanical force to ensure uniform particulate fusion. These precisely engineered dosages carry significant metabolic weight once they enter the human digestive system. This measurable biological impact is the explicit reason for the required warning label, not recommended for children and pregnant women. The primary active payload, caffeine, acts as a potent central nervous system stimulant. This schematic compares the resulting physiological response. In the adult physiology on the left, the standardized dose safely and temporarily blocks fatigue receptors in the brain, generating stable electrical pulses for short-term performance enhancement. However, due to a child's lower body mass and still developing neurology, the exact same manufactured dose overloads their system. The concentrated stimulant rapidly elevates heart rate, degrades baseline focal capacity, and causes severe sleep disruption. A secondary metabolic parameter dictates caution regarding the high sucrose payload. Consuming these highly concentrated, rapid absorption energy spikes routinely creates compounding biological risks, particularly accelerated obesity. Consumer safety warnings are not arbitrary legal texts. They are strict, heavily researched biochemical boundaries directly mapped to the engineered payload of the product. This technical layout shows the automated lab monitoring required at the end of both operational pipelines. The readouts verify the strict acidity and sucrose levels for liquids, while structural dimension scans validate the integrity of every solid tablet. Whether a facility is stabilizing a complex aqueous solution or mechanically compressing a dry powder, the ultimate objective remains identical: flawless chemical consistency. Modern mass-market consumables operate at the precise intersection of biochemistry, thermodynamics, and mechanical force, engineering biological effects at an industrial scale.